All right, so this next theorem is called the first derivative test for critical points. And essentially what it says is, let's say we have a sine graph here for the first derivative, okay? And let's say we found two critical points of the function, x equals a, x equals b. And let's say we have 0, and maybe this one was d and e. Because a critical point is where the first derivative either equals 0 or does not exist. So, and let's just say we take some sample points and we found that the first derivative went from positive to negative to positive, let's just suppose. Well then, effectively, what we can do is think about what the graph would have to look like. Well, if we have a graph that is going uphill and then sort of flattens out, so we have a horizontal tangent at the top, that's what a derivative of 0 is, a horizontal tangent, and then it's going to decrease. So this right here tells us that our graph sort of has this basic shape. It increases, flattens out, decreases. So that means there has to be a local max at x equals a. Similarly here, if we are going, we are decreasing and then increasing, now a little different here. In the middle, we don't actually flatten out. The first derivative doesn't exist. So this could mean a couple different things here. It can mean a couple different things. If, let's suppose for this, let's suppose that x equals b is in the domain. Of f, and actually let's rephrase that and say, let's suppose that f is differentiable, or let's say continuous. Let's go ahead and say continuous. Is continuous on all real numbers. Then what this means is our graph would probably have the shape of something like this. Maybe like that. Something like that. That could definitely happen. That could definitely happen. So you see, it's d and e because the left-hand slope is a negative number, the right-hand slope is a positive number. It doesn't round off and flatten out nice and smoothly. It just has this sharp transition from negative to positive. It doesn't actually pass through 0. This would still be a local min, though, in this case. So really, the important thing is if our function goes from positive to negative, we're going to have a local maximum. If it goes from decreasing to increasing, we're going to have a local minimum. So let's take a look at example 5. So we want to analyze the critical points. So in other words, when we read this analyze, so analyze the critical points essentially means find all the critical points of this function and determine if at those critical points it's a local minimum, local maximum, or neither. Because it is possible to have a critical point, but it doesn't mean you have to be a local min or max. It could just be like x cubed, where the graph flattens out for just a moment and then continues increasing. So there's a horizontal tangent right here at x equals 0, but it's increasing before and it's increasing after. So while this is a critical point, we go from positive to positive first derivative, so increasing to increasing, which means that this x equals 0, although it's a critical point, it is neither a local minimum or a local maximum. So example 5 here, what we're going to do is we'll start off by finding critical points. So we will take a derivative, which is 3x squared minus 27x. Nope, just minus 27. And then, because this is a polynomial, it's continuous and differentiable everywhere, so this exists. We don't have to check or worry about d and e. We just need to see when this first derivative equals 0, and this would equal 0 at x equals plus or minus 3. So this gives us two locations to put down on our sign graph for the first derivative. So we go ahead and label, and we know the first derivative is 0 at these two locations. So now we know that the derivative is either positive or negative in each of these. And it can't change. So if it's positive at every single x value between -3 and 3. If it's negative at every single x value between -3 and 3. So we only need to pick one x value within each region. Think of this as a string, and then we cut it here and here, which creates really 3 distinct regions for us to test within. So we can go ahead and do x equals -4, x equals 0, and over here let's do x equals 4. So now another important thing that we should keep in mind is that we only really care about whether it's positive, the first derivative, or negative. We don't care what value. We don't care if it's -4 or if it's -400. That doesn't matter. The magnitude, the absolute value, the size of the number, the distance from 0, that doesn't matter. It's only what side of 0 are we on, positive or negative. So because of that, there's a nice little thing we can do here. Let's go ahead and take our first derivative here, and let's just really quickly factor this and make it look a little bit nicer. We can go ahead and factor out a 3 and get x squared minus 9, and then we have 3 times x plus 3 times x minus 3. So in factored form, we have something that looks like this. So now this number 3 is just positive, and then we can look at what happens to these two factors here when we plug in -4. So, for instance, f prime of -4, we see that 3 is positive. The next term, if we plug in -4, we're going to get -4 plus 3, which is -1, which is negative. And this term right here will be -7, which is negative. So quick inspection, even if you don't keep track of what the numbers are, we can see we're going to have negative times a positive 3. So positive times 2 negatives is a positive. So this is positive, and we can mark that. Same thing with f prime of 0. Here, it's easier to just look at this format here because the x equals 0 kills this, which means it's 0. Excuse me, it's -27, which is negative. But now, for f prime of 4, same thing. If we look down here, we're going to have positive times positive times positive, which is positive. So now we can see that we go uphill, we flatten out with a horizontal tangent, and then we decrease. So this means we have a local max here. And then here we're going to decrease, flatten out before increasing again. So we've got a local min. So I usually do something like this, so that it's very easy to see that we have a local max and a local minimum. So then we'll just summarize and say local max at x equals -3, and we have a local minimum at x equals +3. And there we have analyzed all of the critical points.